All right, let's dive deep into the world inside your electronics. I'm talking about your phone, your laptop, pretty much everything you plug in. We're going to explore this secret, microscopic world of the power converters that make it all tick. And it's a world that's surprisingly full of tiny waves, hidden rules, and yeah, moments of pure chaos. So it really all boils down to this one question. We think of the power in our gadgets as this perfectly smooth, steady stream of juice. But the truth? It's actually always in motion. It's got these tiny waves that can be an engineer's absolute worst nightmare, or their most powerful tool. And figuring out those waves, that's the key to everything. You see, in a perfect world, that DC voltage would just be a flat, perfect line on a graph. Easy. Simple. But, well, we don't live in a perfect world. The way these converters actually work, the way they move energy around, means the reality is a little more wavy. And here's the kicker. This isn't some mistake. It's not a flaw. This little triangular wave you see here, that's actually the signature of the converter doing its job. Inside, switches are flipping on and off thousands, even millions of times a second, storing and releasing energy, and that's what creates this constant rise and fall. This little variation has a name, and it's called ripple. And honestly, the best way to picture it is to think of the main DC voltage as this big, steady ocean tide. The ripple, that's just the small, predictable waves riding right on top of it. It's always there, and engineers have to design around it. So how do you actually measure these little waves? Well, you use something called the ripple ratio. It's just a percentage that tells you how big the waves are compared to the tide. A tiny ripple ratio means you've got a super stable output. A large one, well, that's where things start to get really interesting. And look, this isn't just some abstract theory for a textbook. The size of that ripple has a huge direct impact on the physical design of every single electronic device you own. It literally dictates the size, the cost, and the performance of the parts inside. This puts engineers in a constant tug of war. If you want a super stable output with almost no ripple, you have to use big, bulky, and expensive components. But of course, we all want our gadgets to be smaller and cheaper. The way you get there? You switch faster. The higher that switching frequency, the smaller and cheaper you can make the components. And this is where we get to the heart of it. Okay, so we can manage a small ripple, we can balance it. But what happens when things change? What if the power your device is drawing gets really, really low, and that carefully balanced ripple suddenly becomes way too big for the tide it's riding on? This is the moment everything flips on its head. It's when the converter can cross a critical threshold and enter a totally new state of being, a place where all the old rules just don't apply anymore. Okay, so let's paint a picture. Scenario 1, you're pushing your laptop to the max. Maybe you're gaming. The average current is really high. That triangular ripple wave is just riding comfortably on top, never even getting close to zero. This is the normal, predictable state. It's called continuous conduction mode. But now, you close the lid, your laptop goes to sleep, the power it needs plummets, so the average current drops way, way down. But here's the crucial part. The size of the ripple wave itself doesn't change, so the whole thing just shifts downwards, getting dangerously close to that zero line. And then, at a really light load, it happens. The bottom of the wave, the trough, actually hits zero. For a split second in every single cycle, the flow of energy just stops. The converter has officially crossed a critical boundary. This brand new state is called discontinuous conduction mode, or DCM. Now, discontinuous doesn't mean your power is flickering. It means the flow of energy through a key component, the inductor, is no longer a continuous stream. There's this little dead time in every cycle where the current is just sitting at zero. And believe me, once you cross over into DCM, everything changes. All the nice, elegant, predictable behavior of the converter, gone. It starts playing by a whole new, much wilder set of rules. I mean, the math tells the whole story. In normal mode, CCM, the output voltage is decided by this beautiful, simple formula. It's clean, it's predictable. But in DCM, the formula becomes an absolute monster. Suddenly, the output voltage depends on everything. How much load you have, the size of your parts, how fast you're switching. It gets really complicated really fast. And this isn't just a headache for engineers trying to solve equations on a whiteboard. No. Misunderstanding this jump from the simple mode to the chaotic one can have very real, very physical, and sometimes very explosive consequences. That's a direct quote from MIT professor David Perrault. That's not a movie script. That's a real story. He was working on a converter, accidentally knocked the load off, which instantly threw it deep into this discontinuous mode. The voltage shot up out of control until a capacitor just blew up. That's what's at stake here. Okay, so after hearing a story about exploding capacitors, you're probably thinking, right, so this DCM thing is a dangerous problem we need to avoid at all costs, right? Well, what if I told you it's not the whole story? Turns out this chaotic state has a really surprising and sometimes incredibly useful upside. It truly is a double-edged sword. On the one hand, yeah, it's a pain to control, it can be electronically noisy, and its behavior changes with the load. But on the other hand, it lets you do things that are flat out impossible in the normal mode. Things like getting super high voltages, or, and this is the big one, changing power levels almost instantly. And that right there, that's the superpower of DCM. It's speed, the ability to respond and change its power output on a dime. Let's break that down. Imagine your system screams for more power, like right now. A normal CCM converter, with its low ripple and big, heavy components, it's like a freight train. It takes a while to build up speed. But a DCM converter, with its high ripple, it's like a sports car. It can change its power output and deliver what's needed in the very next cycle. It is incredibly nimble. So for those applications where that split-second response time is everything, I'm talking about things like radio transmitters or high-end computer processors, engineers will actually intentionally design their converters to operate in this seemingly chaotic mode. That complexity is a price they're more than willing to pay to get that incredible performance. Which leaves us with this final question to think about. In this hidden world inside our electronics, is this state of discontinuity a dangerous bug that needs to be engineered out of existence? Or is it a powerful feature, a secret weapon to be controlled and harnessed? And as it turns out, the answer is both.